Before we move to dynamic instabilities, I want to mention my dear friend Dwayne Walliser's work as well in the instabilities or the ideas of how zonally symmetric arguments and dynamic thermodynamic optimizations and feedbacks can be explained in a slightly different fashion. So if there is convergence that is maximum of the equator, then the argument by Walliser and Somerville, I think it's also a 1994 paper, is that that's where convection happens because there is a convergence of moist static energy, but the convergence that's happening near the surface has frictional effects, and that's going to be different on the equatorward side where there is Coriolis is smaller than on the northward side where the convergence is coming from. So that differential which is going to drive under conditional instability in the atmosphere, that's going to drive convection, diabatic heating and further convergence, has a natural tendency to move northward, and as it moves northward obviously friction, Coriolis increases and frictional effects increase, and that can determine the location of the ITCZ. We'll look at something like this a little bit later on. It's slightly different than the arguments made by Mitchell and Wallace, which includes oceanic upwelling and the feedbacks with the coupled feedbacks and so on. So it's still kind of consistency check because they take a shallow water model and put a heat source off the equator and show how it works. But again, doesn't fundamentally explain why convergence is maximum north of the equator and so on. So to head towards that, we need ideas on the dynamic instabilities associated with the cross-equatorial pressure gradient, which we have argued already is important for advection of absolute vorticity. So we're going to create instabilities by eta or f being less than 0. So we said wrong signed vorticity being advected across. So eta is zeta plus f, which is the total vorticity. And distributions of absolute vorticity tell you the complexity of the story. So these are mean monthly 925 hectopascals, so low level zero absolute vorticity lines for the Pacific sector and the Atlantic sector for these various months, just to see how things move. So wherever you have eta less than 0, well, in the northern hemisphere you have eta greater than 0, and in the southern hemisphere eta less than 0. But when you have cross-equatorial transports of eta, you have eta or f less than 0, which are unstable. Okay, they are potentially inertially unstable. As we said, just because you pushed vorticity across doesn't mean you will have convection, because the atmosphere could be statically stable and cap convection. But you can see how complicated the absolute vorticity lines are. These are the various months. So July, obviously everything is north of the equator here, and IPCZ is to the north of it. As you remember, convection happens to the north of the absolute vorticity line, absolute zero vorticity line. And over the Indian Ocean, you get quite complicated region and complicated story. And even though you have eta or f less than 0, strong cross-equatorial gradient and so on, you don't necessarily get convection here because of other reasons that we will look at later on. Okay, because it's basically the atmosphere is stable because it's under subsidence. So if you have air coming down, then no matter what you do below, you're gonna convect and break through that static stability. Okay, and Atlantic, as you can see, mostly remains to the north. As we said, it touches the equator in some months, which makes a difference in terms of the wind anomalies and what happens here at lower frequencies and so on. And the eta equal to 0 line here, we'll see later on, it cuts through the wind divergence and so on. So for the most part, absolute vorticity is negative in the southern hemisphere and positive in the northern hemisphere, increasing in magnitude away from the equator. This general change in magnitude of eta with latitude is best seen in 13.2, which is way behind, so I won't go back. However, 13.3 shows that this rule is broken over wide regions where eta equal to 0 contour strays either southward or northward a few degrees into the summer hemisphere. For example, in the eastern Pacific in all months, and the 0 AV contour is displaced northward of the equator. So here ITCZ remains north of the equator throughout the year, as we saw. Okay. Maximum displacement occurs during July, August, and minimum displacement in the winter months. In the western Pacific Ocean, to the north of the Papua New Guinea, there is a large northward displacement of absolute vorticity 0 line associated with the displacement of the Monsoon Trough. So there is the Monsoon Trough that we talked about before, and that's going to have an impact. Displacements into the southern hemisphere in the western Pacific occur during December, February, producing the great cloud band that we will look at again in the period of maximum amplitude of the South Pacific Convergence Zone, SPCZ. Okay. In the Atlantic Ocean, the 0 contour remains north of the equator during all months, but further poleward in the boreal summer than in the winter. Largest off-equatorial displacement of the 0 AV contour occurs in the Indian Ocean. During the austral summer, 0 AV contour extends to 8 south in the the western Indian Ocean, moving closer to the equator in the east. So it's tilted, like the cloud band. In August, the 0 AV contour assumes its most northerly position near 10 north in the northwestern Indian Ocean. Obviously, monsoon has a much more complicated story to tell. Instability, very quickly, when you have two cylinders rotating, let's say with a fluid between, the outer cylinder has angular velocity omega 2, inner one omega 1, and within the fluid between them, you're going to create a perturbation, move a parcel from R to R plus R, so you're going from closer to being the inner cylinder to closer to the outer cylinder, and you're going to look for angular momentum conservation. Okay, and we will see that if the angular momentum increases, so if the outer cylinder, for example, is rotating faster than the inner cylinder, then the parcel will move easily and be stable, whereas if the outer cylinder is moving much slower than the inner cylinder, then the parcel has to reach the lower angular momentum of the outer cylinder, then you induce instabilities. Okay, this is the story that we'll tell in the next podcast, because this one already got long enough. But just think about that instability, because we are talking about perturbing a fluid, pushing it across the equator, and looking for angular momentum conservation as well.